Hey people, we are again solving a problem from RMO 2023. It says that let n is greater than k is greater than 1 be positive integers. Determine all positive real numbers a1 to an's which satisfy this strange condition. So first, let us try to look at the first expression. So the first expression is, let's try to look at one of the terms with ignoring the summation sign. So the term is k to the power k upon k minus 1 a k a to the power k. Let's also ignore this I subscript to make it easier. So let's try to focus our entire attention on this. Okay, so this can be written as k upon, we divide a to the power k both sides, k minus 1 plus 1 upon a to the power k. Okay, now we apply, what we do is we apply AMGM to the denominator. AMGM to the denominator, how we will apply? This k minus 1 we will write as 1 plus 1 plus 1 plus 1, and this is k minus 1 times plus 1 upon a power k. Notice that this is k minus 1 times, k minus 1 times, and this is greater than equal to k times nth root of 1 into 1 into 1. This is kth root of 2 dot dot 1 upon a power k. And see, a power k is there and kth root, so both of them will cancel each other. This will become equal to k upon a. So we conclude that k minus 1 plus 1 upon a power k is greater than equal to k upon a, and the equality only holds if, remember that in AMGM inequality, equality only holds if all the terms are equal. So the equality will only hold if a power k is equal to 1, which would further imply that a is 1. So equality, let me use a different color for clarity. Equality only if a equal to 1. So this will be an important concept to remember. So let's proceed further. So what this basically means is that from this step, we can further conclude that a is greater than k upon k minus 1 plus 1 by a power k. So this is what we get, and we take a square root both sides because the problem has this very term, and we bring about the subscript I. So square root of ai is greater than k upon k plus 1 plus 1 upon a power ai power k. So we will put a summation sign also. Ai square root, this is greater than equal to summation of square root of k upon k minus 1 plus 1 upon ai power k, and this is equal to n. So what we get basically is that square root of summation of square root of ai is greater than equal to n. Okay, and notice that again by the problem condition we have here, we get that summation of ai is equal to n. So summation of ai is equal to n. So let's try to work out something from these two conditions. So for simplicity, let's call square root of ai as bi. So this basically means that ai we consider as bi square. So our problem condition becomes, notice that square root of ai is defined because ai is a positive integer and square roots of positive integers are always defined. So what these two conditions become is that summation of bi is greater than equal to n, summation of ai, which is equal to summation of bi square, is equal to n. This is what we get. Now, so this is what we had got, summation of bi square equal to n. Now we will prove a very well-known inequality. The well-known inequality is summation of bi square is greater than equal to summation of pi the whole square whole divided by n, where there are n terms in the summation. So this is a very well-known inequality, and there are many ways to prove it. We will prove it using Cauchy-Swartz. So remember the statement of the Cauchy-Swartz says that summation of ai square whole into summation of bi square is greater than equal to summation of ai bi the whole square. So this is the Cauchy-Schwarz inequality, and equality only holds if a1 upon b1 equal to a2 upon b2 an upon bn. This is the equality condition. What we will do is, using this we can prove that summation of bi the whole square into the second term, these second terms I will keep as ones. So summation of 1, which basically comes to n, is greater than equal to summation of bi the whole square, and this summation of 1 is basically equal to n, and if we transpose n that side, we will get summation of bi the whole square is greater than equal to summation of bi whole square divided by n. So from this, let's rewrite it. Notice that summation of bi square is equal to n, and summation of bi whole square, notice the summation of bi is greater than equal to n, so this is greater than equal to n square by n, which is equal to n. So we are using this fact here and this fact here, and because see n and n comes these both sides of the inequality. So because these two numbers are equal, then thus both these inequalities should be converted to equalities. Otherwise, these two can't be equal. This number and this number can be equal if any of them are strict inequality. So we get equality in both of them, and from this condition, summation of bi whole square is greater than equal to summation of bi whole square divided by n. This is the Cauchy-Schwarz inequality, and we know that equality in the Cauchy-Schwarz only holds if ai upon bi is constant. So what was bi in this term in the Cauchy-Schwarz we used? They were basically a bunch of ones. So we can write that equality only holds if bi upon 1 equal to b1 upon 1 equal to b2 upon 1 equal to b3 upon 1, and so on. So we basically conclude that b1 equal to b2 equal to up to bn, and if we square both all of them, this basically translates to a1 equal to a2 up to dot 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 an. So this is one part. And from the second inequality, which is this one, from this thing we can conclude that, notice that this basically hinges on the fact that summation of bi is greater than equal to n, and equality should hold in this case for the above inequality to become an equality. So this is basically equals. And notice that how did we get this expression? This expression we got from this chain of steps, and I had already shown in the beginning that the equality only holds if a equals 1. So we use them on all of ai, so we can conclude that all of ai should be equal to 1, otherwise the second inequality won't hold. So this is what we get. So we were asked to find a1 a2 up to an. So a1 an, this set is basically equivalent to 1 1 1. We showed that all of them are equal to 1. All right, this was the solution. Thanks.